Hello gamers, welcome to another video. Today we will continue discussing the database reversing and exploitation project. This time we'll be discussing the SDB database implementation. So now a bit about the SDB database implementation. It is a hash map database where you have a key which maps to a particular value. Both keys and values are both strings. If you want to store binary non-string data such as data with no bytes, it will base64 encode it, I believe, or something like that. It has interfaces with both a C API and also command line interface tools. There is a link to the project if you want to see it. And so the typical database leaking attack that this project revolves around, I was not able to execute against this database implementation. I will get into why that is later. So a bit about how the database layout is. The hash map this database works off of relies on buckets to remediate hash collision issues. Since there are way more possible hashes than individual spots to put their values, a hash will map to a particular bucket, which can store multiple records, so it can store multiple records at the same spot. There is an array of offsets to buckets in the database. It will hash the key and use that hash to get an index into the bucket array to figure out where the corresponding bucket is. The bucket will contain slots which contain record metadata, specifically the hash associated with the record and the offset to where the record is so it can find it. Now to start looking at how this database implementation works under the hood. First off, I want to show off how the hashing algorithm works. On the right here, we see the SDB hash length function from util.c, which will actually handle the hashing functionality. On the left here is a Python function which effectively does the same thing, it's just in Python. Effectively, how this hashing function works, initializes the hash value to CDB hash start, which is 0x1505, and then it will just iterate through each character of the string, running it through this formula, which effectively has addition, binary shifting, XORing, and ANDing, which we also see that right here. And then afterwards, this value left over will be the hash. Now, let's get into how the database selection algorithm works. First, I will show off some code that references the database API to do these operations. Here on the left, we see insert records.c, which will use the SDB set function to actually insert records. These records will have the key value be key 0, key 1, key 2, and the value or the record being stored being value 0, value 1, value 2. On the right, we have getRecords.c, which will simply just retrieve the value stored at the record with the key being key 0 and print it. And we can go ahead and over here and compile these two source code files. When we run insert records, we see that it actually generates the database file videodb, and when we go ahead and run get records, we see it will print off the value 0 record using SDB get and puts. So now to show you where the actual logic happens for retrieving a record from the database, we will start off with the SDB get function, since that is the API call that we make to handle this operation. The actual logic that we are interested in happens a little bit further down the call stack, but in SDB.c, we see that SDB get effectively just wraps the SDB get length function call, which you see that right here, which we see it basically just calls SDB constant get length and then runs startup on the return value from that. This function right here, the startup, will become extremely relevant later on, but you see it basically just wraps this function right here, SDB constant get length, which we see that function corresponds to this one right here. It has a bit more logic in it. However, after reversing it, I found that the function or the piece of code that we really care about right here is this CDB find next function call right here, which we find that function in CDB.c right here, the CDB find next. And this right here is the actual logic that we care about for handling the database selection logic. Okay, now we're going to go through in depth how the internal workings of the CDB find next function is, which is actually responsible for locating the record in memory. It takes 4 arguments, the first being a struct pointer to a struct that models a portion of the database, second being the 4-byte hash of the key, the third being a pointer to the key, and the fourth being the length of the key. And we're going to run this getRecords.c binary in a debugger so we can actually see it. We should break within the CDB find next call within the CDB get. So it should be looking up for the key 0. And we go ahead and launch it in GDB, break there. And we see, what do we see? Those are the registers. Let's check RDX. RDX is the key, a pointer to the string key 0. RCX is 4, which is the length of key 0, so those 2 arguments are what we'd expect it to be. Looking at the second argument, RSI, we see that it is this integer here, OX7C751342. Over here is a Python terminal where we've just declared a function that replicates the exact hashing functionality within CDB, and when we hash key 0, we see that we get the same integer hash, so that is what is to be expected. Now, going through here, we see the first thing that it does is it calls CDB read, where the position is the hash shifted over by 2 and ended by 1023. When we go ahead and do that, we see that it gets the offset OX108. Also, we see that it's reading it into the char buff, which is 8 bytes. And what is buff sc? Pretty sure this is just 8 bytes. So let's go ahead and just quickly break there and check that. See what's going on there. Continue. Okay, yeah, the size is 8 bytes, and it is scanning it into this buffer right here. I'm going to go ahead and view it real quick. Okay, right now it is this piece of memory, but it's going to change. Let's actually, this is the database file right here, open video DB, that was created with insert records.c. Let's actually go to the position OX108, which is, give me a second. Okay, it is here. I can tell it is here from this offset value right here. And it is reading in 8 bytes. So we see there is the 4-byte integer 0440. It is that way because it's the least significant byte first, and followed by the 4-byte value 0450. Let's go ahead and finish, or I'll wrap up this CDB read call. And we see it is the 2 values OX0440 and OX0450. Now, looking through this, we see that what it will do is it will unpack these 2 4-byte values and store them into, the first one is into C-H position, and the second one into position. And looking through this, what we can tell is that these 2 4-byte values are actually offsets to the bucket itself, particularly the start of the bucket and end of the bucket. So when we go to the spot in the database between OX0440 and OX0450, right here is where OX0440 starts, and right here is when OX0450 starts. So these OX10 bytes right here make up the actual bucket. Now, looking through here, we can see that here is where we actually have non-null bytes. So this is a slot within the bucket that is actually occupied. We can also tell that this bucket can hold 2 slots here, which we also see that in the code. To find the number of slots, it will just subtract the end from the start and divide it by 2 times the size of U232, which is 8. So the portion of this code right here, it's just trying to get the bounds of the bucket. Here is where it actually will iterate through the slots within the bucket to actually find that. We see that we'll call another CDB read, where it is calling it from whereas reading in 8 bytes from the bucket itself. We see here it will unpack the later 4 bytes as the position and the first 4 bytes as the new hash, which you see right there. And then what it will do is it will see if that hash matches the actual provided hash, and if so, it will call this match function, which will check if the key stored at the record pointed to by the bucket slot actually matches it. And let me get into a bit what I mean from there. We see here the first 4 bytes is 0x7c751342, which matches the hash right here that we get, 0x7c751342. So the hashes match. It's going to then check if the actual entries match. We see here that the offset here is 0x0410. So when you actually go to 0x0410, which is right around here, we see as the start of the record first it's 0x05 followed by 0x07, 0x05 being the size of the key plus a null byte, 0x07 being the size of the value plus a null byte. And then we see here is actual key 0 and value 0. So you can see it actually will use that offset to get the offset to the record. And yeah, that is in depth how it'll actually will take a key and actually resolve it to find where the record is in memory. So now going back to the reason why I was not able to actually execute the database leaking attack against this database implementation, going back to the SDB constant get length function, the CDB findNext function, which we just covered, that isn't responsible for actually scanning in the value of the record we're looking for. It's just responsible for locating, does this actually exist, and if so, where in the database file is the value or the offset to the value. This SDB constant get length function, what it will do is we'll take the position found and add it to a pointer of the in-memory replica of the database file. So it will return a pointer to in memory, the start of value 0, and we can see that here in GDB. Let's go ahead and set a breakpoint. Run it. Let's go ahead and finish this. And we see right there is the return value. And we see here it returns a pointer to value 0. But beyond that, we can actually see the rest of the database file. We see 0x0507 followed by 6b6579, which we see that is the start of the next record, 0507, 6b6579. And we can also see what appears to be some of the other buckets and stuff. So the return value of this SDB constant get length function is the actual is a pointer to the in-memory file. Now the issue is it's calling stirred up on this pointer, which what stirred up will effectively do is it'll just malloc another block of memory, and in this case copy bytes from the input string until it reaches a null byte. And that null byte is really what is killing this, because when a new record gets inserted, from what I'm seeing, null bytes are getting inserted, and I haven't found any real way around that. If that wasn't an issue, I could leak data. Like, let me just go ahead and show you right here. I'm just going to overwrite it with a bunch of zeros. So this value 0 is just one solid string leaking into key 1. And we can go ahead and just run this, and we see that, oh hey, value 0 leaks into key 1. But because of the issue where in the database implementation here, it inserts null bytes into the records as they're created, I don't really see any way that this attack could be meaningfully executed. But yeah, thank you for watching this video. That is it for now.